Welcome to Scene 1. Today, we begin our exploration of one of the most fundamental concepts in computer science, Big O notation. As you hear these words, notice the title Big O notation being written at the top of the screen over the next 2 seconds. Big O notation is vital because it provides a way to describe the worst-case scenario of an algorithm's performance. Think of it as the safety net that tells us the maximum amount of time or space an algorithm might need under the most challenging conditions. Now, let's break down the core components. First, the definition. Big O is the most common asymptotic notation used in algorithm analysis. Second, its purpose. It measures the worst-case algorithm complexity, giving us an upper bound on the running time. Finally, its significance. Big O is essential for algorithm analysis. It informs us about performance and guides us in optimizing our code. Welcome to Scene 2, Fundamentals Explained. In this segment, we delve into the core principles behind Big O notation, a tool essential for understanding worst-case scenarios in algorithm analysis. As you watch the left side of your screen, notice the diagram unfolding. Each rectangle represents a distinct step in an algorithm's execution, linked by arrows that indicate the flow of operations. Now, let's turn our attention to the right side, where you'll find a neatly arranged column of definitions. Here we have key Big O notations. O1 stands for constant time, ON signifies linear time, and ON2 indicates quadratic time, often encountered in worst-case performance. Watch closely as we now highlight one of the algorithm steps. The circumscribed block represents a particularly intensive section, a worst-case scenario, and simultaneously, the ON2 notation in the definitions column is emphasized. This dual highlight shows that certain algorithm steps can lead to a significantly higher computational complexity. On the left, you see a series of graphs, and on the right, corresponding bullet points that define our complexities. O1 for constant, ON for linear, and ON2 for quadratic performance. Notice how we maintain a clear visual separation, ensuring you always see the complete picture without overcrowding the screen. Let's begin with O1, the constant time complexity. As this curve appears, notice the steady horizontal line. It indicates that no matter how large the input gets, the performance remains unchanged. Now, moving on to ON, the linear complexity. Here, as the diagonal line is drawn, it illustrates that execution time increases steadily with the input size. Each additional unit of input adds a proportional amount of work. Finally, we look at ON2, the quadratic complexity. The curve now takes on a parabolic shape, visually emphasizing how the computation skyrockets as the input grows. Big O notation is an invaluable tool for worst-case analysis, and these performance curves visually anchor the abstract concepts we introduced earlier. Keep in mind how each pattern informs design choices in computer science projects. Welcome to Scene 4, Algorithm Analysis. In this segment, we transition from abstract comparisons to concrete examples by diving into real algorithm cases. Here, we see the title Algorithm Analysis emerging at the top of the screen, setting the stage for our discussion. Let's begin by examining a simple linear search algorithm. In the center, you see a flowchart. Each box in this flowchart represents a fundamental step of the algorithm, from starting, comparing values, checking if the item is found, to concluding the search. Take a moment to follow along as each step is revealed in sequence. Now, to the right of the flowchart, we have corresponding pseudocode blocks. Here we present the logic in code form for both linear search and bubble sort. As these blocks fade in, arrows appear linking specific lines of code to the associated steps in the flowchart. These arrows act as a visual bridge, guiding your eye from the abstract algorithm flow to the concrete implementation details. Next, let's look at how we derive the worst-case complexity. Next to the pseudocode for linear search, observe the appearance of the complexity label O(n). A brief transform animation illustrates how a simplified snippet of our code morphs into this Big O expression. This transformation emphasizes that linear search scales linearly with input size. After a short pause, a similar process reveals the label ON2 for bubble sort, indicating its quadratic worst-case performance. Building on what we have seen so far, notice how each animation and visual cue is carefully timed. The brief pauses allow you to absorb each detail before we transition to the next concept. Let's now move on to a quick summary of the key points: the algorithm's step-by-step flow, the mapping of code to action, and the final Big O notation that tells us about performance in the worst-case scenario. Now, moving into Scene 5, we embark on a deeper analysis with our example titled Advanced Big O Analysis. As you see the title gracefully appear, imagine this as the gateway to understanding how even complex algorithms are methodically broken down for worst-case analysis. Here, our diagram begins to take shape. Notice the first component, our initial node, labeled with the formula Tn equals Cn log n, representing the main computational work. Watch as this node, along with its companions, appears sequentially. Now, let's focus on a critical point. Notice the highlighted section, our edge case analysis. Here, a circumscribe animation draws your attention, while an annotation explains why this case demands special consideration. Each step has been carefully arranged with clear spacing and safe margins, turning a daunting problem into manageable steps. We now conclude our advanced analysis by fading out the diagram and title.